All right. Well, thank you everybody for coming today. You braved all the snowstorm and all the attractions of spring break to make it through here. I'm very happy today to welcome Rachel Mandelbaum from Carnegie Mellon University to visit us. Rachel is a well-known expert in the subject of weak lensing, and I think the thing that of the many things that make her work remarkable, she's done a really wonderful job of merging a very deep understanding of the pixel level problems that confront weak lensing, but has gone all the way through to very perceptive analyses of how the lensing signal is telling us about the galaxies themselves, but also possible modifications of gravity and other examples. Rachel has had a decidedly mid-Atlantic sweep of her career. She got her PhD at Princeton working with Rosh Selzak, and then took a Hubble Fellowship at the Institute for Advanced Study, and then had a couple more years as a postdoc at Princeton before moving to Carnegie Mellon as a professor. And so really glad you're here and looking forward to hearing about the cosmology with the Hyper Suprime-Cam survey.
Thank you for the warm welcome. So as you just heard, I'm going to tell you about cosmology with the Hyper Suprime-Cam survey, HSC. So I'm going to start by telling you about HSC, the instrument, and the survey that's being carried out with it, before transitioning to talking more specifically about cosmological applications. Before I get started, though, I want to note two things. The first thing is that I'm going to be talking about a data set, a decent chunk of which is now public. So if anything that I'm saying sounds very interesting to you, I would encourage you to Google HSC Data Release 1 and play with our beautiful data. The second thing I want to say is I once confused an entire audience for like 20 minutes because they thought I was saying HST, Hubble Space Telescope, and I was saying HSC. So as a guidepost, HSC is always Hyper Suprime-Cam, and if I want to talk about the Hubble Space Telescope, which I actually do want to do, I will say Hubble. Okay, so HSC is an instrument on the Subaru telescope, which is located on the summit of Maunakea. So it's a prime focus instrument, so it sits all the way up here. Okay, so just to give you some context of what is HSC, why is it such a powerful instrument? If you're going to do a cosmological survey, so you would like to cover a large area at a reasonable rate, so you don't take too much telescope time, and you also want your images to be nice and deep and sharp. So you need a wide field of view. Before HSC existed, the previous imager was called Suprime-Cam, and so this is an example of a typical Suprime-Cam image around a galaxy cluster located here. Okay, so on the one hand, this image is nice and big. If you were to do a cutout here, there would be a single Hubble field of view like that in the middle. So clearly, this can cover a nice area comparable to the full moon. Nonetheless, if you calculate how long it would take to carry out a large cosmological survey with that instrument, it's really prohibitive. So along comes HSC, 1.5 degree diameter field of view, so it doesn't even fit on this sky. So this nice wide field of view instrument was essentially built to enable large survey science to happen with an imager at Subaru. So this is an example of one of the early HSC images during commissioning of the instrument. Okay, so this is basically a single pointing, so this isn't a combination of multiple images, this is just a single pointing. And Andromeda, we can cover basically the entire thing. At the same time, there's a lot of pixels on this camera, so we can zoom in to the red box and zoom in further to the purple box. And you see there's a lot of really nice detail. Okay, so it's 0.168 arcsecond pixels, and the seeing at the site is excellent. So we have really nice high resolution images. So a survey was envisioned and was proposed called the HSC SSP survey, the Strategic Survey Program Survey. Okay, so, and it essentially has a wedding cake structure. So there's a wide survey that covers 1,400 square degrees. Then there's a deep survey, which goes a magnitude deeper, but it covers less area. And then there's an ultra deep survey that goes another 0.7 magnitudes deeper than that, and is, just 2 pointings. Okay, so if we ask where does the HSC survey fall in the context of other things that are happening, in terms of large imaging surveys, then we can look at this plot. The horizontal axis shows the area of the survey. The vertical axis shows the R-band depth, so a deeper survey is higher up on here. And that means the march of progress in the field is towards the upper right corner. Right? We're moving towards larger area surveys that are also deeper. Okay, so the ongoing surveys are the magenta ones, plus red is HSC, the wide, deep, and ultra deep layers. And you can see that in the context of ongoing surveys, HSC is not the largest area survey. There are several that are larger area, but it's among the deepest ongoing survey. Right? It's on an 8-meter telescope. You can easily go quite deep in a reasonable amount of time. Okay, and so HSC is, in some sense, you can think of it as leading along these arrows towards LSST, which is going to happen in the 2020s. Okay, so this is a survey that uses multiple broadband filters. So for most of the science I'm going to talk about, it's these GR-IZ-Y bands that are relevant. There are also narrow-band filters that are used in just the deep and ultra-deep survey layers to enable detection of Lyman alpha emitters at specific redshifts. So the band passes are shown here, and mostly they're these broadband filters, but also the few peaks for narrowband filters. So what's shown here is the total exposure time for the wide survey layer in the top row, deep and ultra-deep. Total exposure time meaning if you consider all exposures that are taken at a given point, it adds up to this many minutes of exposure time, so 20 minutes of I-band exposure at a given point, spread out across 6 or 8 exposures, I forget right now. And you can see the time really adds up as you get towards the ultra-deep survey. Okay, so this plot shows where the HSC survey fields are. So basically, these dark red fields are the HSC-wide survey fields, and so you can see they're centered around declination of 0. So basically, one of them is on stripe 82, and then there's this one that covers well-known fields like cosmos and gamma. So the survey fields were selected based on a few criteria. First of all, we wanted to have a complete overlap with SDSS. That's because SDSS provides not just, so there's much shallower imaging, but also a spectroscopic sample that's very interesting to analyze in concert with the deeper HSC survey imaging data. But there are other interesting multi-wavelength data sets in these areas, like the ACT CMB survey and other ones so we're basically trying to produce multiple scientific synergies through this multi-wavelength data set. And in addition, the spread in right ascension means that we can essentially observe all of our, observe at least one field in pretty much any month without having to go to really high air mass. So as an observational issue that this spread is kind of deliberate. Okay, so this survey was proposed in 2013. So with 170 COIs, it was the largest ever galaxy survey at Subaru, and 300 Subaru nights were approved by the community in 2013. Okay, so this survey is a big deal to the Japanese astronomical community. It's using a lot of telescope time at their amazing telescope resource, and there's a lot of the community that's very involved in the survey science. And so the survey started in March 2014. So if you do the math, actually just going back here, 300 nights in 5 years. So that sounds like we should be getting 30 nights per semester for 10 semesters. The survey start was gradual. It was a ramp. So we started with 1.5 nights in a semester, then 12 nights, and 15. That turned out to be really beneficial to us because as the instrument, any new instrument has issues at first, filter exchange problems and other things, and we didn't end up losing a lot of time to all of that. We had a slow ramp, and then once everything was working smoothly, we went to our target 30 nights per semester. So by mid-2017, half of the survey's time had been allocated. And this plot just gives you some idea what some of the very early data looked like. So since the cosmos field has been observed, by Hubble, a nice area with ACS data, very high resolution imaging, and then there's been a lot of other multi-wavelength imaging, we said, well, why don't we, look there? Let's do some early imaging there. So this is one of the early multicolor images. This is based on 2.5 hours of time in the RIZ filters to build up this nice color image. So you can see, okay, first of all, it is a color image, right? We have multiple bands. And you can see, it's a deep image, nice resolution, and so on. This is the corresponding Hubble image, which was based on about 500 hours, however many, 640 orbits. So that's a single band image at even higher resolution. But you can see, the resolution on the right is clearly higher than with HSC, but, HSC is still quite nice imaging. And of course, it took us a lot less time to get this. So the image quality is extremely nice. So this is a beautiful instrument, and so we're essentially our image quality is dominated by the atmosphere rather than by the instrument, PSF. So this is a plot showing the distribution of the seeing size in the I band for our first year of data corresponding to like 130 square degrees. So the black curve is over that whole area, and the colored curves are for distinct patches because our coverage was not a contiguous 130 square degrees. It was in a number of patches. So you can see the median seeing was 0.58 arcseconds, which is pretty amazing. I grew up working on the Sloan Digital Sky Survey and did weak lensing with the SDSS, and the median seeing that I dealt with was 1.2 arcseconds. So double this, except really it's the area that matters, so 4 times this. So this is the kind of thing that makes weak lensers like me drool. This is amazing. Okay, so there is a little bit of a trick here. We did optimize I-band observations towards preferentially good seeing. So the median seeing for the survey across all bands is closer to 0.7 arcseconds, which is a bit worse than this, but not exactly something to sneeze at. Okay, so that's the end of my basic introduction to the HSC instrument and the survey and the data. And I would really encourage you to check out our data release site. We have a lot of really exciting data for people to play with. So now I'm going to talk a bit about my own scientific interests, gravitational lensing. So just starting as a basic introduction, so gravitational lensing is the deflection of light by mass, including any gravitational mass, so whether it's visible or dark. So we have some distant object, here's us, and in the case of strong lensing, the light has taken multiple pathways, and so we see multiple images of the object. And so it gives rise to beautiful features like this. These are strong lensing arcs inside of a massive cluster around the brightest cluster galaxy and some other massive objects. And again, the key thing about this is that this is a way for us to measure the gravitational potential of all the matter in this massive lensing object, right? So including the dark matter. I always start with a strong lensing picture because it's beautiful, but that's not actually what I do. So I measure weak gravitational lensing. Okay, so you could think of this as kind of an opposite extreme. Strong lensing occurs when you have a serendipitous, superposition. You have one object almost directly in front of another, with such a close association that you get multiple images. But if you have something that's not directly behind another object, it's still propagating through a space-time that, has been affected by masses along the way. And so there are smaller deflections of the light rays that have a smaller effect on the light profile. We don't see multiple images of every object on the sky. But their light profiles have all been slightly affected by gravitational lensing. So it's the opposite extreme from strong lensing in the sense that weak lensing happens everywhere. But it's not a visually striking phenomenon where you can look at something and say, I see the weak lensing on this. So it's something we have to measure as a statistical phenomenon. So the basic picture here, this is us there's some object over here, the light rays are all getting deflected by some mass, and it smears out the image in a tangential direction with respect to this lensing mass. Okay, so we see something which is smeared out. And of course, we don't know what its original shape was. But what we can see is that any objects near here will have been smeared out in a similar way. And so there are correlations between object shapes that are induced by weak gravitational lensing. The strength of the lensing effect depends on the amount of mass in this lensing object, how far away the lens and source are on the sky, and how far away they are along the line of sight. So the picture you could have in your head is, imagine if you had an idealized screen of perfectly round galaxies that are really far away from us. So this is that screen. And then ask, what would this screen look like if I put a bunch of really massive lens objects in front of it? What would happen to the apparent shapes and positions of these perfectly round sources? So the answer is, you would get smeary patterns in the shapes. So someone like me who's used to thinking about weak lensing would look and say, aha, I see, a kind of circular pattern here. There must have been a lensing mass in front of this point in between, and that's why we got a smeary pattern there. There's a lens in front of here, so we get a smeary pattern. If you have things pointing radially towards a point, that means there's an underdensity there. But the key thing is, of course, these two galaxies are near the same lensing mass. They got smeared in the same way. And so we get all these coherent patterns. So looking at this picture, you might say, that is very nice, Rachel, but galaxies are not round. Right? Galaxies are not perfect circles. Okay, so this gets back to what I said before. Of course, we don't know that galaxies are round and every aspect of their shape is determined by lensing. Rather, galaxies already have intrinsic shapes, and there are tiny distortions in those shapes induced by lensing that we cannot see by our eye. Still, if we correlate huge numbers of galaxy shapes, pairs of galaxy shapes over millions, tens of millions of galaxies, those patterns from here will emerge. Okay, so again, we measure lensing statistically. Okay, we look for coherent shape distortions. The magnitude of the lensing shape distortions are typically a percent, meaning something that was originally round would have an ellipticity that's around 0.01 or even less after weak lensing. But the intrinsic shapes are more like 0.3. So we need to beat down the noise induced by these intrinsic galaxy shapes in order to measure these tiny lensing distortions. So that sounds like a lot of work. But there are a lot of reasons why you should care. There are a lot of reasons why I enjoy measuring weak lensing. There's a lot of distinct science applications that you can do. So I wanted to briefly describe those here. Okay, so, excuse me. Okay, so first of all, there is the context of just our universe, right? Our universe today, we know that sort of 4 or 5% of the universe is described by the standard model of particle physics, and the rest is kind of embarrassing, right? We don't really know, we don't have a theory that says, what is dark matter, what is dark energy, right? So dark matter has gravity, there are a lot of theories for what it could be, WIMPs, supersymmetric theories, and so on, but we don't actually know. And similarly, dark energies essentially are a way of explaining the accelerated expansion rate of the universe, but there is not a good theory that describes what that's due to. So from what I told you before, you already know that weak lensing is a way of statistically mapping out dark matter, the location of dark matter in the universe, because the lensing distortions are sensitive to all of the matter, including the dark matter. Okay, so what about dark energy? So this plot over here is essentially an illustration of structure growth. So the leftmost box is a simulation box with dark matter particles, and the density field in this is not completely smooth. And then as you move to the right, these are boxes at later and later times as structure has grown due to gravitational collapse. So the box on the right is this webby structure we call the cosmic web. So dark energy affects the rate of structure growth because it causes this accelerated expansion rate of the universe. So if we measure not just where is dark matter in the universe, but we measure how has structure in the dark matter evolved as a function of time, we're measuring structure growth, and that gives us a way to learn about dark energy. And indeed, weak lensing is one of the most powerful ways to learn about the properties of dark energy. So those are my top two things up here. But there's more. Okay, so this picture illustrates our basic idea for where do galaxies live, right? You see a galaxy, and you know there's stellar mass associated with it, but galaxies live in extended dark matter halos that have a much larger extent than just the visible parts of the galaxy. So if you imagine identifying some nearby objects, you can say, okay, I want to pick a bunch of nearby spiral galaxies or elliptical galaxies, and you measure the lensing distortions that they cause in stuff around them, then you can essentially probe the matter distribution, the average matter distribution around your foreground lens objects. So if you want to understand the connection between galaxies and their dark matter halos, for example, what's the average relationship between galaxy stellar mass and dark matter halo mass, weak lensing is an ideal way to do that as well. And that's relevant because if you're interested in the processes underlying galaxy formation and evolution, these galaxies don't grow up on their own. They grow up with this association of dark matter with them. And so understanding their dark matter halos is a key part of resolving questions in how galaxies have formed and evolved. Excuse me. And finally, we can use weak lensing to constrain the theory of gravity on cosmological distance scales. Okay, so we're all familiar with the idea that on solar system scales, general relativity is king. It seems to describe things extremely well. But it hasn't been really tested that stringently on scales corresponding to tens of megaparsec. Gravitational lensing is an ideal way to do that. And so in current surveys, we've placed constraints on essentially on gravity and how close is it to general relativity with sort of 10% precision. Future surveys will be able to get that down to about 1%, which is going to be extremely useful in sort of distinguishing between dark energy and the potential for it actually being modified gravity. Okay, so those are the things that I'm really excited about measuring using imaging surveys like HSC. So I thought I'd tell you just a little bit about how this measurement actually works. So there's a measurement called cosmic shear. Cosmic shear is essentially a measurement of weak lensing by large-scale structure. In other words, by that cosmic web, right, all the matter between us and distant sources. So what this picture shows is a projection. The red and white is the projection of the density in a simulation, a cosmological simulation of structure. So the white are the highest density points. Those are galaxy clusters. And the red is medium density, and black is under density. So the blue ellipses show the direction of the lensing deflections, the lensing distortions that a galaxy behind this matter distribution would see. And so you can see, for example, these two galaxies that I'm pointing to, they are behind this filamentary structure. They're both lensed by it, so their shapes are aligned. Whereas if we consider a galaxy in the bottom right corner and upper left corner, it's lensed by mostly different structures, and so there's less correlation in the shapes. So to measure this, we require the galaxy positions on the sky and with some kind of measurement of this lensing distortion, an estimate of the lensing distortion. But the final ingredient we need is, if we want to interpret this in terms of mass and structure growth, we also need to know the distances to these distant source galaxies in order to convert the lensing distortions into some measurement of cosmic structure. Even more powerful is what's called tomography. So what tomography is if you take a galaxy sample. So in an imaging survey, you don't have redshifts. You don't have spectroscopic redshifts, but you hopefully have photometric redshift estimates. And you can divide up galaxies into those that are more nearby and those that are more distant. So in this example, they have 6 bins in photometric redshifts. Shown here. So, a lower redshift bin around 0.3, the highest is around 1.2. This was in the CFHT lens survey. So what's even more powerful than lumping all the galaxies together is to split them up in these bins and correlate the shapes of galaxies within and across bins. In other words, take the galaxies in bin 1 and correlate their shapes with each other. They are closest to us. The light rays have passed through less universe on the way to us, so the lensing shears are lower. Whereas bin 6, if you correlate the shapes of galaxies in bin 6 with each other, they've passed through a lot more universe, they've been lensed more, and so the shear correlations that we see are higher. So by splitting up into these bins and correlating galaxies within bins and across bins, we can measure how structure has grown with time. So later on, I'm going to show you a measurement that's in progress of cosmic shear tomography, this redshift-dependent lensing measurement with the HSC survey. Before I do that, though, I wanted to tell you about another type of lensing measurement for which I'll also show you a measurement in HSC called galaxy-galaxy lensing. So this is something I alluded to earlier. You pick some lens objects that are closer to you, and maybe you choose them because they're interesting and you want to know more about them. Or maybe you choose them because they're really massive and you think they'll have a large lensing signal. So this red one is a massive lens object. And you measure the lensing shear distortions in a tangential circle around the lens objects. So you need a sample of background galaxies where you've measured their lensing distortions, and you need some estimate as well of how far away they are, again, to interpret the lensing distortions in terms of mass in the foreground object. So if you do this, you can effectively measure an average mass profile around these foreground lenses, where the mass you're seeing is any overdensity associated with that lens. So if the lenses live in dark matter halos of a certain mass, then you would see effectively the mass profile of those dark matter halos. So this is now a relatively old example of what that looks like. Again, I'll show you something in HSC later. This is a plot from SDSS. We took massive luminous red galaxies, and we measured the lensing shears of those galaxies, the lensing distortions, and effectively get a sort of projected mass profile as a function of separation. So if you look at the distance scale here, we're going from about 50 kiloparsec. So that's outside the light of the LRGs, not by a huge amount, but outside their light profile. We're in their dark matter halos. And we're going out to 50 megaparsec, which is far beyond the typical extent of a dark matter halo. Right? So this, few hundred kiloparsec is the typical extent of a dark matter halo. The reason the profile doesn't just cut off after that is, of course, cosmic structure growth. If you have a bunch of massive things like massive dark matter halos, there's other stuff gravitationally attracted to that. And so you get this gradual fall off where the nearby stuff is in the dark matter halos associated with these LRGs, and the far away stuff is more distant structure that is nonetheless correlated. Okay, so that was a generic introduction to weak lensing measurements. Now I'm going to tell you about what we're hoping to do with them in HSC. So if we want to measure structure growth and say something about dark energy, so the typical number we'd like to say something about is the equation of state of dark energy. So a cosmological constant would have an equation of state of -1. We'd like to constrain the equation of state as a function of redshift to say something about, does dark energy look like a cosmological constant or not? Okay, so this plot shows a forecast of how well we should be able to constrain dark energy once we have the entire HSC survey area as a function of redshift. So the red curve shows our expected 1 sigma uncertainty on the equation of state of dark energy. And so you can see there's some sweet spot around redshift 0.7 where our constraints are the tightest. The constraints are, they're weaker below that. That's because of the limited area of the survey. We just don't have that much statistical constraining power. And they're weaker as you go to much higher redshift again because we don't have as many sources in the very distant universe to measure the lensing deflections there. If you compare this, again, in context of ongoing surveys, so dark energy survey is a 5,000 square degree ongoing survey that is shallower than the HSC survey. And what that means is that this plot, it has a similar U shape, but it's shifted a bit to the left. If you have a very large area survey, you can measure structure growth more effectively at low redshift. That's why dark energy survey does better at low redshift than HSC. But you can't see galaxies as far away as HSC can. And so at high redshift, you get more powerful constraints from HSC. So these surveys in design are complementary in the sense that one is shallower but larger area, the other is deeper and smaller area, and that also corresponds to being somewhat complementary in what they can say about cosmology. So that was what we expect to get for measurements of structure growth using cosmic shear. So this slide is about what we expect to do with galaxy-galaxy lensing, measurements of lensing by massive foreground objects. So what's shown here on the left is an image from the Sloan Digital Sky Survey, which is about 4 magnitudes shallower than the HSC survey. So we see this image, and you see there's this kind of lonely looking red galaxy in the middle with the arrow pointing at it. So that is a galaxy that was targeted for spectroscopy as part of the Baryon Oscillation Spectroscopic Survey, BOSS, around redshift 0.54. So these were basically, massive red galaxies at intermediate redshift that were targeted to measure baryon acoustic oscillations. And as I said, in the SDSS image, they look kind of lonely, right? There's not so much stuff associated with them. And so if we now have an image with Subaru that goes magnitudes fainter, deeper, we can see, well, there's actually kind of a lot of stuff around there. Right? This is the exact same galaxy, but it has friends. Okay, so Subaru, the HSC survey is going to essentially, fill in what are the other, galaxies associated with these CMAS galaxies, these galaxies from the BOSS survey. And beyond that, we can measure background galaxies. So CMAS galaxies are around redshift 0.5. The typical redshift of sources in HSC is more like 0.8 or 0.9, which means that we find a lot of stuff behind the CMAS galaxies, and we can measure galaxy-galaxy lensing by these BOSS galaxies, these massive red galaxies. And by correlating the BOSS galaxy power spectrum with this lensing signal, we can essentially measure structure growth. Okay, so HSC Data Release 1 happened last February, so at this point, like 13 months ago. It has a lot of different types of data products, so image, catalog level products. There's a really cool sky map that you can zoom around in. I sometimes go there to check out some weird thing I found in the catalog and then sort of start playing around. It's really fun. That's 100 square degrees, data in all 5 bands to full depth. Full depth meaning the full wide layer depth of HSC survey. There's some deep layer data as well. And we just had a PASJ issue that has a lot of technical and science papers from the survey that came out earlier this year. So at this point, I wanted to transition to showing you some of our results. Okay, so if you want to do a large cosmology survey, you want to know what's in your catalogs. Right? You have catalogs of galaxies and stars, and you want to understand how are those measurements made, and do they reflect reality? Okay, so the HSC team uses the software pipeline that's being developed for LSST. We're essentially doing a shakedown cruise on real data. Okay, so that pipeline is described in a paper led by Jim Bosch that was on the archive last May. The image I'm showing you here illustrates one of the ways we characterize the catalogs that are produced by the LSST data management pipeline on HSC Data. So what we do is we basically take the real data. Real data, of course, has a lot of interesting and challenging features to deal with, detector defects and so on. And we insert fake galaxies into it. So we insert fake galaxies into it. So this was an original image with detections circled in green. This is after we stick stuff into it. And there's a difference image over here with the new detections circled. Okay, so we've put fake stuff into the real data. That's kind of a convenient simulation trick because if you try to simulate the survey from scratch, you need to know all about a lot of details of your detectors and the atmospheric PSF and everything else, but that's already in the real data. So stick stuff into your real data. It already has, a lot of messes in it, and then you can check how well do I recover what I put in. So what we found by and large is that the LSST software pipeline performs extremely well. At star-galaxy separation, at galaxy photometry. It did highlight one interesting challenge that's going to face the HSC team and the LSST team, and that's blending. Okay, these are very deep images, so we see a lot of objects, and light profiles are starting to overlap. So you can see this problem illustrated in this plot. So what we did is we know the true input flux, right, or magnitude. We compare our measured flux minus our input flux. So the ideal in the absence of noise or any biases would be this 0 line. You can see there's a lot of scatter around the 0 line. Scatter's okay, right? We know there's noise in real images. But you notice there's a tail up here that's systematically, going off in one direction, so that doesn't look so hot. So what's going on over there, I haven't told you what the x-axis is. That's a quantity we call blendedness. It's the pipeline's way of quantifying how close is this object to another object, what fraction of its light profile might overlap with another object. To the right is a very high degree of blendedness. This log 10 blendedness of -1 means something like 10% of the pixels of the flux seems to overlap with another object, and the bias is happening in the high blendedness region. Fortunately, most of the galaxies, while blended at some level, are not that severely blended, and so we can still recover the fluxes very well. So by and large, what came out of this paper was really good news for us. We know how to analyze our data robustly, and that's also good news for the LSST survey, because this is their software pipeline. But there was this cautionary note that we do need to learn how to deal with this blending problem better, and I'll get back to that later. Okay, so this slide just shows a little bit about the Shear catalog that we're going to use to measure weak lensing from the HSC survey. Okay, so, oh wow, that's so weird. There are numbers on axes on my screen, but not here. Okay, so I will just tell you the main message of that plot. This shows the average galaxy number density as a function of the seeing size. So in other words, to the left is better seeing images. To the right is worse seeing images. We can measure the shapes robustly for about 24 galaxies per square arc minute over in good seeing, or going down to 20 for our worst seeing images. Of course, our worst seeing images are not that bad. This is 0.7 arcseconds out here. So for someone like me who grew up in the SDSS, I had a number density of 1 galaxy per square arc minute. So HSC is so amazing, and this plot, when I saw it, it's super exciting. This is actually after some fairly conservative cuts. We eliminate galaxies fainter than an I-band magnitude of 24.5. It's challenging to get photometric redshifts for them, and we want to do our first cosmology analyses without them. There's some other plots here that show how we characterize systematic uncertainties and ascertained that we could carry out a weak lensing analysis that was not dominated by systematics. But given the time, I'm not going to talk through those plots. I'm happy to discuss with anybody later. So this slide shows some nice plots from a paper led by Masamune Ogori. So the basic idea, as I mentioned to you earlier, is that weak lensing lets you figure out where is mass, like all the mass, dark matter and light. So the top plot shows a mass map. Basically, taking this catalog, covering this large area, you can essentially map out where is the mass. And so the lighter the color, the larger the mass, the darker colors are underdensities. So the bottom is a map that was made in a similar way, but just by counting up the total stellar mass in luminous red galaxies. So you can immediately see there's clearly some correspondence between the mass peaks here. In other words, if you have a lot of LRGs, you have a lot of mass overall. There are a few corresponding peaks and also some corresponding decrements. Clearly, the correspondence is not perfect, and we expect that for a few reasons. First of all, of course, there's noise. There's a lot more noise in this lensing map than in this stellar mass map. Second, not all the mass in the universe is in LRGs. Some of it's in other stuff. Nonetheless, the correlation coefficient between these maps is around 1/2, which is roughly what we expect given the limitations due to the reasons that I mentioned. So mass maps look really cool. When people have a new survey, it's very tempting to say, okay, I'm going to make a mass map. And then the question is, what can you do with it? So one thing you can do with it is actually, sounds kind of boring, but it's really important. You can test for systematic biases. These lensing shear measurements involve, accounting for the effects of the PSF on the galaxy shapes. That's a very kind of fiddly thing to do, and we'd like to know we've done it right. So we can take our lensing map, and we can make an analogous map for anything that we think can generate a systematic bias. We could make a map of the PSF size, make a map of the PSF ellipticity, the air mass, any observational parameter that we think should not really correlate with lensing mass, and then take the correlation between them. So what's shown up here is exactly that exercise. Basically, so you see this point is 0. The points correspond to correlations with different maps, where one of the maps is the lensing map, and one is some observational effect that we don't care about, and we don't want to affect our lensing measurements. So ideally, the measurements should be, these correlation coefficients should be 0 within the noise, and they are. This point up here is clearly very non-zero, but that is the only real correlation. That is the correlation I mentioned before between the total lensing mass and the stellar mass for LRGs. So that is something that we do expect to be significantly detected, and it is. So this plot is very good news for us. It means we can go off and do weak lensing cosmology with this data set. So again, in the interest of time, I'm going to jump ahead a little bit. Okay, so I wanted to talk a little bit about image simulations. So people who work on weak lensing really like making image simulations. The reason for that is simply, like as I said, we have this kind of fiddly measurement to do. We want to measure these tiny lensing shape distortions. There are a lot of other things, detector effects in the PSF that modify galaxy shapes, and we'd like to be sure we've corrected for all those effects. So if we make an image simulation, we know what true lensing signal we put into it, and we can make sure that we've covered it. So one of the things we learned is related to what I mentioned to you earlier about the impact of blending. So we learned that the way you make your image simulations for a deep survey like this really matters. So what this plot shows is the apparent size of the galaxy compared to the PSF. So what 1 means is a galaxy is infinitely resolved. It's enormous compared to the PSF. There are not many galaxies like that. And 0 means it's totally unresolved. This is basically a star. It looks like a PSF. Okay, so for all of the objects in our simulations and in our data, we measure this resolution parameter. And ideally, we would like our simulations and data to look alike, because that tells us we've simulated a realistic sample. Okay, so there's a black curve over here, and there are blue curves. So the black curve is the real HSC survey data, and the blue curves are one set of simulations, and these red curves, which look terrible, they look nothing like the data, is another set of simulations. So the natural question to ask is, what's wrong with the red and pink simulations? Why do they look so bad? The answer is the effects of blending between objects were included in the simulations shown in blue that match the data. Whereas for the red and pink curves, we simulated isolated objects. It turns out that something like 20% of the galaxies in this survey are what we called unrecognized blends, meaning they are probably 2 objects that are so close that we didn't even recognize that they're 2 objects, and we just measure them as one thing. And that one thing is going to be poofier than the individual objects would have been. And so the entire galaxy size distribution gets modified by that. And we need to include that in our simulations if we want them to look anything like real data. So this is again on the theme of blending matters for these deep surveys. Okay, so now I'm going to show you some ongoing work. So when I agreed to give this talk, we thought that we were going to unblind our cosmology analysis, meaning we're going to, open up the box and see what cosmological parameters we were getting in December of 2017. So I figured I can give a talk about this in March. we have not opened the box yet. So I'm going to show you some results that are blinded, meaning you can't read cosmological parameters off of them, but I will nonetheless try to convey the story of what we hope to learn and what is the broader context in which we're learning this. Okay, so this is kind of a busy plot. This triangle plot shows the cosmic shear tomography. So this is this cosmic shear in redshift bins, where 1,1 is lowest redshift bin correlated with itself, 4,4 is highest redshift bin correlated with itself, and then you have all these cross bins. Okay, so these are power spectra. These are pseudo-CLs for those who are familiar. Excuse me. And so you see on each plot, there are red points which are significantly non-zero, and then there are yellow and blue points which are consistent with 0. The yellow and blue ones are supposed to be 0. So the yellow ones should be 0 due to symmetries, and the blue correspond to features that wouldn't be generated by lensing by large-scale structure, but they can be generated by systematics. So the yellow and blue being 0 is basically a sanity check, and the red is the thing that we really care about and want to model. So the overall amplitude here doesn't actually mean anything. In other words, all of these curves have been rescaled by an arbitrary factor that we don't actually know, generated through some random seed. It's the same factor on all of them, so the relative amplitudes are relevant and physically meaningful. And in particular, we expect that as we go towards the upper right, the signals will get larger, and they do. So that's a good sign. And the total signal to noise of this measurement exceeds 20. I think our latest estimate is that if we consider just essentially the overall amplitude of the matter power spectrum, we can constrain that to something like 3 or 4% using this measurement. Okay, so as I said, we have not unblinded, so I can't tell you cosmological parameter estimates, but I will tell you why this is so interesting. So this is a table that I took from a paper produced by the KIDS survey, which is another ongoing imaging survey that's measuring lensing. Okay, so basically, the horizontal axis is this quantity that lensers call S8, which is a combination of the matter power spectrum amplitude and omega matter, which happens to be, the S8 is essentially the best constrained quantity from a weak lensing measurement. So our error bars on this should be smallest of any cosmological parameters. And so the different points are just different measurements of S8. So the blue is an S8 measurement from the KIDS survey in this Kollinger et al. Paper, which used power spectrum measurements. Red is also KIDS survey, but using correlation functions. So correlation functions are just the configuration space correlation between pairs of galaxies. You wouldn't nominally expect them to differ very much from the blue, and the reason they differ is it has to do more with them emphasizing different sets of scales in the two measurements. Okay, so this is the KIDS survey. Then we can jump down here to this point. This is CFHT lens. That's an earlier survey, less constraining power, so the error bars are bigger. You can see it basically agrees with the KIDS red points. So the thing is, they use the exact same analysis software. So if there's something funny going on in the analysis software, KIDS and CFHT lens should do the same thing as each other. Okay, then this point, this is another lensing survey, DLS. That's kind of off to the right, so higher amplitude, interesting. Planck is over here. Right, so Planck is also off to the right. So when you hear weak lensing people talk about tension with CMB, what they're talking about is the fact of essentially that the KIDS data up here and CFHT lens seem to have a lower amplitude of the matter power spectrum than what you would get from Planck data. And of course, the DLS people, deep lens survey people, will say, not so fast. We don't disagree. Maybe KIDS and CFHT lens did something wrong. So there's some sign of tension. The statistical significance is not very large. It's sort of 2.5 sigma. So it could simply be statistical fluctuations. It could be some low-level systematic that's not been accounted for, or it could be a sign of some interesting physics. Okay, so in the interest of time, I won't say much about this, just that people have been noticing recently that if they allow more freedom, so instead of lambda CDM, cosmological constant, if they allow the equation of state of dark energy to vary, it can relieve some of the tension between lensing surveys and CMB. Okay, I'm going to skip forward again. So just to conclude with lessons learned, and again, interest of time, I'm going to skip to second lesson. So this is an image from the HSC Ultradeep Survey, not the wide survey, which is the origin of the lensing results I showed you, but the Ultradeep Survey. And the key thing that's striking in this beautiful image is that there's stuff everywhere, just everywhere, right? There are objects. And so this really highlights what I raised earlier, the point I raised earlier about the importance of understanding how blending between the light profiles affects our measurements. You know, we're carrying out these very powerful surveys, and they have the potential to tell us a great deal about cosmology and about galaxies, but we do have this sort of barrier to get over. We have to understand what is the impact of the blending effects seen here. So just to give you some numbers associated with this image, this is just a quote from the HSC pipeline paper led by Jim Bosch. In the wide layer of the HSC survey, 58% of all objects are members of blends. Objects and members of blends means that there is an association of objects that was flagged as having things with light profiles that seem like they could overlap, and it requires special handling of that system. So it doesn't mean they're right on top of each other. It could be that there's just a little bit of overlap at the edges. Nonetheless, that requires special handling, and that's 58%. And in the deeper layers, like the ultra deep layer, that's 74%, which is not too surprising when you look at this image. Okay, so if we think about future deep surveys like LSST, blending is one of the major challenges that might require us to think differently about, about the way we interpret our measurements. And so this is a key problem that the cosmology community has to confront in the coming few years. And you might say, okay, so I'll just concern myself with space surveys. Thank you very much. But Euclid, W1st, will use ground-based images to get photometric redshifts. Right? You're not going to do 5 bands of optical imaging for space. You're going to do whatever you need to do for space and get your multiband optical imaging from the ground. And so understanding how to combine those higher resolution space-based images with lower resolution ground-based images is going to, again, require confronting this blending issue. So these data are really beautiful. And fortunately, we know about this problem now. And so one of the key things we'll be doing in the coming years is understanding how to deal with this better. And indeed, there's been a lot of work already on improved methods of deep blending for LSST just in the past year, inspired in part by what we have found in HSC. So, lots to do, but people are already working on it and getting some promising results. So to conclude, the HSC survey had its first data release a year ago. I highly encourage you to play with our data. It's really beautiful data. And the HSC map, this zoomable map that we have online, is really fun to play with. There's a lot of science being done, so keep an eye out on arXiv. We hope that in another 2 months or so, some of those cosmology results that I gave you a little preview of will be out on the arXiv. And we're learning valuable lessons for the era of precision cosmology. Thank you.
Okay, let's have some questions. Here.
Given where you expect to be around the time of the launch of Euclid, let alone W1st, how much of an improvement do you expect Euclid to represent over what you're doing?
You mean in terms of constraining power, or?
Well, constraining power in your particular area of lensing.
Right. Okay, so Euclid is going to be quite powerful for weak lensing. It's going to build up that constraining power pretty gradually, though, because their strategy basically is, you could imagine covering the whole area shallower and then, building up depth, or you could imagine doing a small area to full depth and then adding area gradually. Euclid is doing the second of those, and that means that its statistical constraining power sort of just builds up linearly with time. So the full Euclid data set is going to be, tremendously more powerful than what we can do with HSC, but it's going to take a while to get there because of the survey strategy.
How much of the blending is intrinsic versus functions of PSF?
That's a great question. Yeah, if you look at a very deep space-based image, you can see that blending is relevant, but it's less of a problem than in ground-based images. So basically, you can think of axes. Like if you go to greater depth, blending effects are more important because more stuff is popping up out of the background. Or at fixed depth, if you have worse seeing, then again, blending effects are more important. So both of those things are relevant. Within the distribution of seeing for a survey like HSC, the variation in blending effects is across the survey is definitely noticeable. You can see the blend rate changing as a function of seeing, but it's not a very sharp change as a function of seeing. It's more that we've just gone to these quite deep images, and that's what's driving much of what we see.
In your mass map versus your light map, there was at least one or two very white spots, very high mass dot regions, which had very little stellar light coming out. Was that interesting?
So in principle, it's interesting. The question is, what are the noise properties of the map at that point? I know we've had some cases where it seemed like there was a fluctuation, but really what was going on was that there was a bright star mask there, and so there was the signal to noise there was preferentially low, and we just had a fluctuation. So that's the kind of thing where you would look for those, and then you would take the image and go, what's going on here? And sometimes it just seems mysterious and worth investigating, and sometimes you say, that was a noise fluctuation.
So there were some interesting ones.
Yeah.
Good.
Rachel, it would seem if the blending issue is a systematic flaw currently, that there's some trade between going deep and going wide. And since the HSC survey is not an all-sky survey, are you adjusting the survey strategy to go shallower over a wider area, which is what that would sort of suggest?
Yeah, that's a really good question. So we have not adjusted the survey strategy. There are a few reasons for that. First of all, there are some science cases that use the HSC wide survey, but they really like the depth and they're not as worried about the associated systematic errors. Another reason is if you do the cost trade-offs, like doing a shallower survey, given the readout time, it's just not super efficient. So, I think.
But there's an optimization there.
Yeah, there's definitely an optimization. But the other thing that we're counting on is that our analysis is not limited by the current state of the art in the blending. That there's a lot of active work on that, and so if 2 years from now, like we're analyzing the full survey instead of this subset, we'll also be doing much better on the data that I just showed you. And so we're somewhat counting on the fact that the state of the art has to improve, and there's a lot of effort going into that. And so we will benefit from that.
So you mentioned a lot about deep blending. Do you find that intrinsic source structure, like spiral arms or anything like that, is an issue?
Yeah, so structure is always kind of an issue for deep blending. And I think when I was a first-year grad student, people were very concerned because the SDSS deblender was shredding massive galaxies that had a lot of structure in them, and there's a lot of, we just tore up all the big galaxies. It definitely is an issue, and it also, that issue has sometimes led to, preferentially different deblending treatments in different scenarios. Like you might have a different deblender for, say, cluster regions. You might have, you might have some afterburner that looks for big galaxies that got shredded. That is a challenge. For weak lensing, we're mostly, we want to build up a high number density of objects, so we're using, pretty relatively small, faint things. So it's not so much stuff that would get shredded, And we sort of more have the opposite problem, that we're worried that we have these unrecognized blends that it didn't even recognize there were two peaks and treated them as one object. And that's kind of, for my science, that is actually more of a problem than shredding.
Any last questions? Okay, let's thank Rachel.